Hello, I'm Tom.
And I'm Mia.
Welcome to the Adaptix podcast. You know, this is our series where we turn these really advanced ideas in artificial intelligence and robotics into, well, simple, clear explanations. I mean, we all know this field moves so fast, and a lot of the time it can feel pretty overwhelming. So our goal is just to create a space where anyone, and we mean anyone, can build their understanding at their own pace. Doesn't matter if you're just getting started or maybe you're exploring the broader world of intelligent systems. Let's dive in.
In this episode, we want to explore what it really takes to engineer machine learning systems reliably, from how we evaluate models to how we make sure they work in the real world.
It's such a critical distinction to make, because for so many people, the world of machine learning seems to stop the second an algorithm is trained.
Right. They see the cool new architecture or maybe this incredible accuracy score.
Exactly. But in any mission-critical application, we're talking healthcare, finance, infrastructure, anywhere failure has a real cost, that's where the real work begins.
After the training.
Well after. The whole process of evaluation, it's not just a final grade. It is the absolute non-negotiable step that determines if a system is trustworthy.
So it's about moving from a beautiful science project to a piece of industrial machinery.
That's the perfect way to put it.
That makes perfect sense. So we're stepping back from the, let's call it the art of building a model, and focusing on the rigor you need to build a system people can actually depend on.
The whole life cycle, not just one flashy moment.
The whole life cycle.
So when we talk about ML engineering, we really are talking about the system's entire lifespan.
From beginning to end.
From the first moment you're gathering requirements and prepping data, all the way through development, application, and then the really long tail of implementation, maintenance, and monitoring in a live environment.
So it's a holistic view.
It has to be. The most complex part of the system is often the infrastructure you build around the model, not the model itself.
So if training the algorithm is just one piece of that puzzle, what's the practical difference in how you approach it? Say, moving from a cool proof of concept to an actual clinical grade system.
Well, the stakes just go through the roof, don't they?
Instantly.
Take a clinical grade application, something that's helping a doctor with a diagnosis or a treatment decision. A model failure there isn't just a bug.
It's catastrophic.
A misdiagnosis, a wrong resource allocation. The consequences are severe. So building these kinds of mission-critical models, it demands these very specific, highly documented processes. It requires the utmost rigor.
So the focus shifts.
Completely. It's all about safety, efficiency, and making sure every single decision the system makes is scientifically informed and, well, defendable.
I remember reading about a foundational case from the early days of AI in medicine that really drove this point home for a lot of researchers. It was kind of a career-defining lesson for many.
You must be talking about the pneumonia port project.
That's the one.
A classic early example. The objective was incredibly high stakes. Build a model to predict mortality from community-acquired pneumonia.
And the challenge.
The challenge was immense. They were working with a single discovery dataset. So the temptation, the risk of the model becoming way too specialized to the quirks of that one dataset was extremely high.
You mean overfitting?
The ultimate risk. If they had overfit, they would have built a model that looked like a genius in the lab.
But would fail completely with the very next patient who walked in the door.
Disastrously.
So the real lesson wasn't just about getting a high accuracy number. It was about the process they used to validate that number.
Absolutely. The rigor was in the safeguards. The research team was insistent on using advanced validation methods, things like a nested cross-validation design, specifically to kill the risk of overfitting.
To make sure the results were actually scientific.
And generalizable. It really highlights a critical mindset. When the lives are on the line, you have to approach modeling with a healthy dose of paranoia about methodological errors.
So it's robustness over perceived performance.
Every time.
And that gets us to the absolute core of the issue, which is trust. I mean, if a scientific claim can't be independently verified, how can we possibly trust it? And that's where reproducibility comes in.
Reproducibility is, I would say, the foundational dimension of trustworthy AI. We define it as the possibility for another researcher anywhere to take your experiment.
So the original data, the code.
The original data, the original code, the whole documented analysis pipeline, and get the same, or at least very, very similar results. If a finding is irreproducible, it just kneecaps any effort to build reliable systems.
Especially in those safety-critical domains.
Right, where human welfare could be harmed by a false claim.
Why is this so uniquely challenging in machine learning? more so than, say, traditional software development.
The complexity is just an order of magnitude higher. With traditional software, same input, you're almost guaranteed the same output.
It's deterministic.
But in machine learning, you have so many moving parts that all introduce variability. The specific version of your source code, the algorithm's parameters, even subtle differences in hardware like GPUs can introduce non-determinism.
Not to mention the data splits, the dependencies.
The sheer volume of it. You miss documenting just one thing, the random seed, for instance, and the whole experiment can become impossible to repeat exactly.
So the goal is to create this sort of digital artifact, something completely self-contained and fully documented.
Precisely. If you don't document everything, the code, the specific data version, the exact environment set up with all the libraries, the experiment just becomes a ghost. It happened once, but no one can prove it.
But when it is achieved, it creates enormous confidence.
Tremendous confidence. A great example of this comes from pharmacology, from evaluating antipsychotic medications. Researchers there used not 1, but 5 international randomized controlled trial data sets.
Wow.
And these data sets were meticulously documented and shared. By building their experiments on that shared standardized foundation, they made reproducibility far, far easier.
Because everyone agrees on the data and the procedures.
Exactly. It shifts the scrutiny away from the data and onto the conclusions themselves.
That focus on reliable shared data is the perfect transition to the model's ultimate mission, generalization.
Yeah.
We don't just want a model that works in its little controlled lab.
We need it to work everywhere else, and that is the ultimate test of value.
Right.
A model's true performance is never, ever defined by how well it did on the data it saw during training. That number is inherently biased. It's flattering, frankly.
So the real measure.
The real measure is how it performs on new, unseen data. That's what we call generalization. And if a model doesn't generalize, it might be a beautiful piece of math, but operationally,
It's useless.
useless.
And this search for generalization throws us right into that classic tension.
Mm-hmm.
The bias-variance trade-off. Overfitting and underfitting. Can you walk us through those pitfalls with a simple analogy?
Let's use the classic student studying for a history exam.
Okay, the classic educational pitfall. I'm with you.
So underfitting is the student whose model of history is just too simple. Maybe they think everything is driven by a single cause. They just glanced at the textbook.
They failed to capture the complexity.
Exactly. Their model has high bias because they didn't learn the core lesson. So when the test asks for nuance, they fail. They miss the big picture.
Okay, too simplistic, high error. I get that. So what's the other extreme?
That's overfitting. This is the student who is way too complex. They have memorized every footnote, every single date, even the publisher's notes in the margins of their specific textbook.
So they're learning the statistical noise.
The irrelevant patterns specific to their training data. So on a practice test, using questions from that book, they get a perfect score. This leads to these wildly, unduly optimistic estimates of performance.
But then the real exam comes along.
With questions framed just a little differently, and they fail miserably. This model has high variance, it's brittle, its performance just collapses if you show it something even slightly different.
Some high bias means you're too simple, you miss the signal. High variance means you're too complex, you learn the noise. And the goal is to find that sweet spot in the middle.
That's it. For any given problem, there's an optimal model complexity that balances those two forces and minimizes the total error. The entire structure of ML engineering is designed to help us find that sweet spot.
Without cheating and looking at the answers before the final exam.
Exactly.
Which means we have to talk about data splitting. This feels like the foundation of any honest evaluation. How do we set up the data to make sure we get an unbiased estimate of performance?
Rigorous data splitting is basically a 3-part partitioning. It's all designed to protect the integrity of that final performance estimate.
The 3 sets.
First up, the training set. This is the bulk of your data. It's the material the algorithm uses to learn the relationships and build the initial model.
Okay, that's the textbook.
Exactly. Second, we have the validation set. This is the key piece used during development. It's not for building the model structure, but for tuning its complexity, or what we call hyperparameters.
So for example, if I'm building a decision tree, I'd use the validation set to decide how deep the tree should be.
Precisely. Or if you're building a gradient boosting machine, you'd use it to decide the optimal number of iterations. You'd watch the performance on the validation set, and you'd stop training just before it starts to get worse.
It would be a sign of overfitting to the training data.
Exactly. The validation set gives you that constant feedback during development about where the optimal complexity is.
But wait, If I keep tweaking my model and checking it against the validation set over and over, aren't I just starting to overfit to that set too?
You absolutely are, slowly but surely. Every time you iterate and check, you're injecting a tiny bit of information, a tiny bit of bias into your process.
And that's why the third set is so critical.
This is why the test set, or the holdout set, is treated as sacrosanct. It is locked away. You use it only once, at the very, very end, to estimate the model's final generalization error. That one single-use check is the only way to ensure the number you report to the world is genuinely unbiased.
I can just imagine the pressure. You spent months building a model, you run that final test, and the results are just, okay, the temptation to just tweak one little thing and run it again must be huge.
And that temptation is a critical pitfall. It's what we call analysis creep.
Analysis creep.
It's this non-rigorous iterative modeling where you're subtly adjusting things based on what you saw in the test set. By doing that, you're polluting that crucial, unbiased estimate. You're effectively overfitting your entire development process to the whole data set.
So what's the defense against that, especially in high-stakes research where you have to iterate?
That's why, in clinical work or when data is scarce, we have to use these really complex protocols. One is called repeated nested n-fold cross-validation.
Okay, that's a mouthful. Let's try and unpack that. How does it protect the final assessment?
Think of it like this. Standard cross-validation rotates the data, so every piece gets to be the test set once. But nested means there's an extra layer of insulation.
Like a box within a box.
A perfect analogy. The outer loop is for the truly unbiased performance estimation. That's your final test. The inner loop is where all the development happens. The training, the validation, the hyperparameter tuning.
So you have complete development cycle happening inside a protective shell.
Exactly. And when the whole process is done, the final performance is the average of all the results from that outer loop. It creates these methodological walls that let researchers iterate 100 times in the inner loop, all while protecting the outer loop data from ever being seen.
And the result is a truly unbiased error estimate.
Despite all the necessary iteration, that's the level of defense high-stakes modeling demands to defeat analysis creep.
Okay, so once we have that rigorously trained and validated model, we need to actually measure its performance. Let's start with classification, where the model is making a binary choice, yes or no, success or failure.
And for that, the fundamental tool is the confusion matrix. It's basically a simple table, but it's essential. For a binary problem, there are only 4 possible outcomes.
Right, let's lay out those 4 corners.
First, the 2 you want. A true positive, TP, where you correctly predict something is positive, and a true negative, TN, where you correctly predict something is negative.
The successes.
Then the 2 critical errors. A false positive, FP, or a type 1 error is when you incorrectly call something positive when it's actually negative.
A false alarm.
Exactly. And a false negative, FM, or type 2 error is when you incorrectly call something negative when it's really positive.
A misdetection.
The most dangerous kind of error in many cases.
And these 4 outcomes feed all the common metrics, starting with the simplest one, accuracy.
Accuracy is just the percentage of everything you got right. It's super intuitive, but it's almost always insufficient and often misleading.
Why is that?
Class imbalance. Imagine you're predicting a very rare disease that only affects 1% of the population. A lazy model that just predicts, no, this person is not sick every single time.
Will be 99% accurate.
But it's completely useless. It has 0 predictive power.
A perfect example of a high number being totally meaningless, so we have to break it down.
We have to look at metrics that tell us about our priorities. Let's start with sensitivity, which is also called recall. This metric asks a simple question. Of all the actual positive cases that were really out there, how many did our model find?
And when would recall be the #1 priority?
It's essential whenever missing a positive case. A false negative is the most costly mistake. Think about a cancer screening test. A misdiagnosis is devastating. You want your recall to be as close to 100% as possible.
Even if it means you get a few more false alarms.
Even then. Now, the other side of that coin is specificity.
The true negative rate.
Right. It asks, of all the people who are actually healthy, how many did our model correctly identify as healthy? If your specificity is too low, you might catch all the sick people, but you also flag thousands of healthy people for unnecessary, expensive, and stressful follow-up tests.
You overwhelm the system.
You do. Now, that brings us to precision.
Where does that sit in?
Precision is about efficiency. It asks, of all the times the model cried wolf and predicted positive, how many times was it actually right?
Okay, so this would be important for something like a recommendation system.
Absolutely. If a search engine gives you 10 results it thinks are relevant, but 8 of them are junk, you lose trust. High precision is key to maintaining user confidence.
So high precision for high-value targets, high recall for casting a wide net. But those two are usually in tension with each other, aren't they?
Almost always. As you increase one, the other tends to drop. To find a balance, we often use the F1 score.
Which is the harmonic mean of precision and recall. Why a harmonic mean, though? Why not a simple average?
Because the harmonic mean heavily punishes extreme values. A simple average might forgive a model that has 100% recall but 0% precision. The F1 score won't. It forces a model to perform well on both to get a good score. It incentivizes balance.
Okay, so since we know accuracy can be misleading, what other measures can give us a more reliable signal, especially when we consider that some agreements might just happen by random chance?
That's a great point. We have to use chance-corrected measures. Cohen's kappa is a very common one. It basically tells you how much better your model is than just random guessing.
So it corrects for that 99% accuracy we saw in the rare disease example.
It does. A high kappa score means you have true predictive skill, which makes it a much more robust measure than standard accuracy.
And what if the two types of errors have wildly different real-world costs? A false positive costs $50, but a false negative costs $100,000.
Then you absolutely must use a cost-sensitive metric, something like the H measure. This is more complex, but it's powerful because it forces you to explicitly define the cost of a false positive and the cost of a false negative.
So it moves the evaluation out of pure statistics and into decision theory.
It's all about optimizing for value and risk minimization, not just correct classifications.
Now, all of these metrics rely on a hard yes or no, but most models give a probability score first. How do we evaluate the model's ability to just tell the two classes apart, regardless of where we set the final cutoff?
That is the genius of the receiver operating characteristic curve, or the ROC curve. It lets us see the model's performance across all possible decision thresholds at once.
And how is that curve made?
It plots the true positive rate or sensitivity on the vertical axis against the false positive rate on the horizontal axis. As you sweep the probability threshold from 0 to 100%, you trace out the fundamental trade-off of the model.
If I want more true positives, I have to accept more false positives.
That's the trade-off. And the single number that summarizes this entire curve is the area under the curve, or AUC.
An AUC of 1.0 is perfect, 0.5 is a random guess.
Right. But the shape of that curve can be even more important than the single AUC number. This is a key insight. You could have two models, both with an AUC of, say, 0.7.
But they could be useful in completely different ways.
Totally different. One model might shoot up really quickly, getting high sensitivity while the false positive rate is still very low. That's a model that's great for high-risk targeting.
Because you can find a spot on the curve with high sensitivity and not too many false alarms.
Exactly. The other model, with the same 0.7 AUC, might only get there because it does well when you're willing to accept a lot of false positives. That model is better for general screening. The shape of the curve tells the operational story that the single AUC number completely masks.
Okay, let's pivot from predicting a category classification to predicting a continuous number, regression. This could be forecasting energy prices or, in one of the cases we looked at, predicting wastewater quality.
The wastewater treatment plant example is great because it's a noisy, dynamic environment. The choice of regression metric there is critical because different metrics prioritize minimizing different kinds of errors.
And that choice has a direct impact on safety and management.
For sure. The two workhorse metrics here are mean absolute error, MAE, and root mean square error, RMSE.
And they both measure error, but they treat large errors very differently. Let's start with MAE.
MAE is the average of the absolute difference between the prediction and the actual value. It's linear. A $10 error is treated as exactly twice as bad as a $5 error.
So it's less sensitive to big outliers.
Right. It's a good choice when your main goal is just to reduce the overall average error magnitude across all your predictions.
And what about RMSE, which seems to be the one we see most often in scientific papers?
RMSE is different because it squares the errors before averaging. And because of that squaring, large errors are penalized exponentially. A $10 error contributes 4 times more to the RMSE than a $5 error.
So you choose RMSE when big mistakes are particularly bad.
Exactly. In the wastewater plant, if a massive short-term pollution spike is the absolute worst-case scenario you have to avoid, you optimize for RMSE.
But if your main concern is just persistent small deviations from the target, you'd choose MAE.
That's the key distinction. Your choice of metric is basically a statement about which kind of error you fear the most.
We also have to talk about the most popular regression metric of all, the coefficient of determination, or R-squared. It's everywhere, but it's often criticized. Why?
Well, R-squared is very appealing intuitively. It tells you the proportion of variance in your target that's explained by your model. An R-squared of 0.95 feels like your model is explaining 95% of the story.
Which sounds great, but it can give a misleading impression.
It's not a direct measure of prediction accuracy. It can be highly sensitive to outliers, and it can be inflated by noise. You could have a really high R-squared and still have a model that makes huge critical prediction errors. It can lull you into a false sense of security.
So it needs to be paired with something like MAE or RMSE.
You need an absolute error measure to get the full, honest picture.
Now, what if we're building models on different scales? Say one predicts flow rate in cubic meters and another predicts ammonia in milligrams per liter. How do we compare them?
For that, we need scale-independent metrics. A good one is the mean absolute scaled error, AAA. It's stable and scale-independent because it compares your model's error to the error of a very simple baseline model, like one that just predicts the last known value.
And the benchmark is simple.
Beautifully simple. If your MAZ is less than 1, your fancy model is better than the simple baseline. If it's more than 1, it's not adding any value. The root relative squared error, RRSE, works in a similar way.
All these metrics are just single numbers, though. And as we saw with the ROC curve, a single number can hide major problems. How do we visually diagnose how a regression model is failing?
We have to look beyond the numbers. The main tool for this is a residual plot.
Which plots the errors themselves.
Yes, you plot the prediction errors against the predicted values. And the pattern in that plot tells you everything about your model's hidden flaws.
So what's the ideal pattern? What are we hoping to see?
You want to see a null linear pattern. Just a random scattering of points like a shotgun blast. No structure at all. That means there are no systematic defects in your model.
And what are the red flags?
A major one is a curved plot. If you see a clear U-shape or a wave in the residuals, it means your model missed a nonlinear relationship in the data. It's systematically overpredicting in some places and underpredicting in others.
Okay, so a curve is bad. What about the spread of the errors?
That's the other big one. If you see a fan-shaped or funnel-shaped pattern, that's a huge red flag. It's called heteroscedasticity.
Meaning non-constant variance.
And it's a critical failure. It means your model is very confident and accurate in one range, say, for low predictions, but its accuracy completely falls apart and becomes wildly unpredictable in another range. The model is confident where it shouldn't be, and this visual plot is often the only way to spot that kind of failure that a single RMSE number would totally miss.
It tells you where the model is just guessing.
Exactly.
We've established these rigorous methods for evaluation. But even researchers who follow all the steps can fall victim to something you called the silent killer of evaluation integrity: data leakage.
Data leakage is, I think, one of the most significant methodological failures in the field. It leads to these wildly optimistic results in the lab that just completely collapse in the real world.
And it's a widespread problem.
Huge. Reviews have found leakage errors across 17 different fields, affecting hundreds and hundreds of papers. It's a major driver of the reproducibility crisis.
So let's define it clearly. How does information from the test set, the supposedly unseen data, contaminate the training process?
Leakage happens when the test set inadvertently influences any part of the model building process before the final evaluation. The model gets a subtle peek at information it shouldn't have. It's like letting a student see the final exam questions before they start studying.
And then claiming their high score proves they're a genius.
Exactly.
What's the most common and serious type of leakage?
The single most common is what we call pre-processing leakage. This happens when you do your data prep steps, like filling in missing values or standardizing your data on the entire data set before you split it into train and test.
So you're calculating the mean or standard deviation using the test set data.
And then you're using those statistics to transform your training data. You've just leaked information about the test set's distribution directly into the training process. The model learns to rely on those contaminated parameters, and its performance just artificially skyrockets.
The Civil War onset prediction research is just a visceral example of this, isn't it?
It's the perfect illustration. In the original work, researchers were using complex models to predict the probability of civil war. But they imputed missing values and standardized their data by looking at the training and test sets combined.
A classic leakage mistake.
And this incorrect procedure artificially squeezed the variable values into a very narrow range. The powerful model, being a powerful model, learned to exploit that artificial pattern.
It learned the signature of the mistake.
It did. The reported accuracy was a wildly overestimated 0.89. When they went back and did it correctly, separating everything, doing all the pre-processing based only on the training data, the accuracy plummeted to 0.73.
A 16-point drop.
A massive drop. It proved the initial high performance was almost entirely an illusion created by leakage.
And besides pre-processing, there's another critical type of leakage when you're dealing with time.
Yes, temporal leakage. If you are predicting the future, it is an absolute ironclad rule. The data in your test set must always be from a later time than the data in your training set.
You can't use future knowledge to predict the past.
It sounds obvious, but you'd be surprised how often it happens. You can't train a stock market model on data from 2020 to 2023 and then test it on data from 2018. The whole thing is invalid.
So the only mitigation is just meticulous discipline and documentation.
It is entirely about process and separation. That's why the movement toward things like model info sheets is so important. They force researchers to explicitly document, step by step, how they ensured the train to split came first, and how every subsequent step was rigidly separated to prevent any contamination. That's the only way to build models we can trust.
We spend so much time making sure our evaluation is technically sound. But a high accuracy score or a low RMSE, that doesn't automatically mean the model is useful. Which brings us to the ultimate question. What's the actual value of this prediction in the real world?
That is the pivot to real-world value assessment. Predicting an outcome is just a means to an end. The end is translating that prediction into tangible value cost savings, improved safety, better clinical outcomes.
Right. If the model is too expensive to implement or causes more harm than good, the accuracy number is irrelevant.
Totally irrelevant.
In a field like healthcare, how do people actually translate predictive accuracy into a dollar value?
Health economics has a really powerful tool for this called the incremental cost effectiveness ratio, or ICER.
Okay.
ICER explicitly measures the economic cost in dollars required to get 1 unit of effectiveness from using the AI. That unit of effectiveness is typically measured in quality-adjusted life years, or
QLY. So ICER connects the prediction directly to an economic return. What exactly is a QL?
A QAY quantifies both the length and the quality of life gained. 1 QAY is 1 year of life in perfect health. So if a treatment gives a patient an extra 10 years of life, but at only half their previous quality of life, that intervention provides 5 QALYs.
I see. So the model isn't just optimizing for a diagnosis, it's optimizing for the path that maximizes the patient's quality of life for the cost.
It's a true cost-benefit analysis, not just a prediction game.
We also hear about net benefit as a measure of clinical utility. How is that different?
Net benefit is more holistic. It factors in not just the predictive ability, but the potential harm or negative consequences the model's application might cause.
So how many unnecessary procedures did it recommend? How much time did it waste for healthy people?
All of that. It forces the engineer to look beyond the statistical ideal and toward the practical, ethical realities of deployment.
Let's talk about the model's boundaries. A model might be 99% accurate on the data it's seen, but what happens when it sees something just a little bit outside of that?
That's the critical concept of the knowledge quay. It's the boundary where the model's performance just falls apart. It degrades sharply, catastrophically.
It goes from high certainty to just making things up.
Exactly. And a high-quality, safe system has to have a kind of self-awareness. It needs mechanisms to know when it's operating near that cliff to ensure it can be used safely.
And what does that self-awareness look like in practice?
It looks like uncertainty quantification. The system shouldn't just give a prediction, it should give a confidence score. If it sees input data that's way outside what it was trained on, it should raise a flag to the human operator and say, my prediction here is high risk. Please use your own expertise.
Rather than just giving a confident but potentially disastrous wrong answer.
That's the key.
And this all highlights how a successful model can still fail when it's integrated into a larger complex system, like a hospital with finite resources.
This is the core issue of system-level ethical considerations. Let's go back to that ICU admission analogy. You build Model A, which is perfect at predicting which pneumonia patients need an ICU bed.
Okay.
And you build Model B, which is perfect for acute asthma patients. You optimize them both individually. But then on one Tuesday, the two models together recommend 20 ICU admissions. But the hospital only has 15 beds.
You have a non-enforceability problem.
Yeah.
The locally optimized models create a globally impossible situation.
Exactly. The system can't follow both recommendations. This requires system-level planning. You have to optimize a multi-objective function that respects ethical principles about how to allocate those scarce resources. The engineer has to think about the model's impact on the entire system, not just one patient.
So this transition from the lab to the messy reality of deployment is just full of risk. How do we test a model safely before its recommendations start affecting real decisions?
We rely on a crucial safety mechanism called sandboxing.
Okay.
This is where you test the model in the real-life live setting, but with one critical rule.
Good.
Its outputs are observed and logged, but they do not directly influence any decisions.
It's running in parallel. A dress rehearsal with no real consequences.
Precisely. It lets you validate the integration, see how it performs under real-world pressure, all without putting anyone at risk. This is so vital that in places like the EU, sandboxing is actually becoming a legal requirement for delivering health AI safely.
Now, when a model is deployed, it's usually just one part of a huge software system with thousands of possible input combinations. How on earth can engineers test something that sprawling?
That is the challenge of the large input space. We use specialized techniques like combinatorial testing to handle it.
Because testing every single combination is impossible.
Computationally impossible. So combinatorial testing uses sophisticated math to select a much smaller but still representative set of test cases.
How does it choose them?
It focuses on ensuring that every pair of input factors and their values gets tested together at least once. By focusing on these two-way or three-way interactions, you can achieve massive test coverage with a much, much smaller number of tests. It's about being smart and efficient.
Okay, so the model is sandboxed, tested, and deployed. It's working perfectly. But the job still isn't done. Why does a model that works on day one often start to fail 6 months later?
Because evaluation doesn't stop at deployment. It just changes focus. The primary problem you face after deployment is performance decay, which we often just call drift.
The real world changes.
The world is dynamic, and your static model becomes brittle over time.
What are the main forms of this drift?
We usually talk about two kinds. First, there's data shift. This is when the input distribution changes. Maybe the hospital gets new sensors that measure things slightly differently, or the patient demographics change. The underlying rules might still be the same, but the incoming data just looks different to the model.
And the other kind.
That's concept shift, which is more insidious. This is when the actual underlying relationship between the inputs and the outcome changes. Maybe a new effective drug becomes standard practice. Now the older relationships between symptoms and outcomes are no longer valid. The concept the model learned is obsolete.
So constant monitoring is the only defense against this.
Absolutely. You need to constantly track the incoming data and the model's performance against real outcomes. It's an early warning system. It alerts the team that the model might need to be retrained or even pulled before its degraded performance causes a major failure.
It ensures the model stays relevant.
And safe.
We started this entire exploration by talking about rigor, and it seems fitting that we end with the process that maintains that rigor across the system's entire life.
And that process is really all about lifecycle documentation. Modern best practices say that ML engineering is defined just as much by its accountability and process as by its algorithms. Traceability is everything.
So what does that documentation include?
It includes clear model goals, comprehensive risk assessments, thorough software documentation of the whole system, and detailed data design documentation, including exactly how you prevented leakage.
This sounds less like a technical requirement and more like a complete governance framework.
That's exactly what it is. And this systematic rigor, this commitment to process, is what separates true engineering from simple modeling. It's what shapes trustworthy, safe, and modern ML systems.
That really brings us full circle. We've walked the entire path from a simple algorithm to a robust system. We've looked at the forensic evaluation tools like understanding MAE versus RMSE and the defenses needed to prevent silent failures like data leakage, all the way through to monitoring for performance decay after deployment.
I think the most essential takeaway is that trust in AI isn't an accident. It's not a technical trick. It's the result of rigorous scientific commitment. Building systems that really work is less about hitting some peak accuracy number in a lab,
Right.
and far more about establishing these robust, reproducible, and context-aware processes that guarantee safe and reliable performance out in the complex real world. The score is only ever as good as the verifiable process that generated it.
A vital reminder that the foundations and the engineering integrity are what truly matter most.
Indeed.
Thanks for listening to the Adaptive Podcast. If you have any questions, feel free to reach out to us.